afternoon, everybody, and welcome to Manure Monday, edition 19. Hard to believe that we are this far along. Just welcome you to this edition, and our topic today is manure additives. This is going to be an excellent topic, looking at manure additives and using them for managing pH, both in storage and in field application for reducing nitrogen losses and so on. We have a great lineup of speakers for that. So just some logistics as we get going here. First of all, I want to say I think the groundhog was correct. At least Wyerton Willie was correct. He predicted 6 more weeks of winter. And when I look ahead to the forecast for this week, I see rain and I see some pretty warm temperatures. So it gives me a hint that winter is on the way out, which I don't think too many people are going to complain about. So reminder that we do ask you to stay muted throughout the session. However, please stay engaged, and you can do that by making comments or posting questions in the chat. And we will look forward to the discussion happening there. This session is being recorded, and like all the previous sessions, can be viewed later on at manuremanager.com. So I want to introduce our speakers today, and I'll tell you, we have 3 different speakers, and the first speaker is Andrew van der Zaag. Now, Andrew is with Agriculture and Agri-Food Canada. Actually, it could get confusing today because I'm Andrew Barry with OMAFRA, and we have Andrew van der Zaag, and then we also have Andreas Gerwin from Germany. So that's a bunch of Andrews, but we'll try and keep that straight. But Andrew van der Zaag, he was unable to actually attend today in person. So he fortunately recorded a 20-minute video, which is excellent. And we will show that first. And then following that, we're going to have our 2 live speakers here go through a presentation. So Andreas Gerwin, who I already introduced here, and Andreas is the sales rep for North America in agriculture with Vogelsang. And we also have Vanya Kobek, and Vanya is the product manager for ag with Vogelsang as well. And so they will follow up the video with their presentation, and they'll also be live in the chat if you want to post questions later on. So let's start with this video. It is about 20 minutes long. And again, welcome to post questions in the chat, and we'll have a great session here. Cheers.
Well, thanks for the invitation to speak. My name is Andy van der Zaag. I'm a research scientist with Agriculture and Agri-Food Canada in Ottawa. And my talk is about manure acidification for emission reduction from manure storages and from manure application. And I want to talk about both methane and ammonia emissions. Methane is a key contributor to the carbon footprint of meat and milk, and ammonia is a major loss of nitrogen from manure management, as well as having some negative environmental implications. So where are these gases emitted? Well, as soon as manure is excreted in the barn, ammonia can be emitted into the air. And when the manure is transferred to a liquid manure storage, it's in anaerobic conditions where methane can be produced, and ammonia will continue to be lost at the surface. When the manure is applied to the field, ammonia is emitted again as the manure is exposed to the air. And this is all pH dependent. So if there's a biodigester, for instance, in the manure treatment system, that's going to increase the pH and potentially increase the risk of ammonia loss. So we see that there's those 3 sources of ammonia emissions. Here's some simulations from a model in the US looking at how those 3 sources, the barn, the manure storage, and the field, stack up. All 3 of these are dairy manure, dairy farm systems, and they all have similar barn emissions. The manure emissions in the first scenario are higher from storage because there's a greater surface area in the storage. But because of those higher emissions, there's less ammonia left when the manure is field applied. In the second scenario, the surface area is lower and the manure storage emissions are lower, which conserves ammonia until it's field applied by broadcasting, which lets that ammonia be emitted into the air. So the net savings overall is not that much. Only in the third scenario, where the manure storage emissions are lower and the field emissions are lower, because the manure is injected into the soil, does the overall emissions of ammonia get substantially reduced. And you can see from the scale here that we're talking about pretty substantial amounts of nitrogen loss from the overall farm system on a yearly basis. So acidification is one approach to helping to conserve nitrogen and reduce ammonia emissions. This comes from Europe, where reactive nitrogen has been in focus for more than a decade. There's a lot of policy focusing on reducing ammonia loss and other nitrogen losses to protect the environment, for instance, the Baltic Sea. And acidification has been identified as a best practice. And it's identified for use in barns, for use in liquid storages, and for use in fields. In Canada, we don't have the same policy focus on ammonia, but we do have now greenhouse gas targets at the government level, as well as more recently targets set by organizations like the Dairy Farmers of Canada, companies like Maple Leaf. So my colleagues and I were considering how could we take this acidification approach and perhaps apply it to helping to reduce greenhouse gas emissions with a co-benefit of ammonia emission reduction that might be better suited to Canadian conditions. So let's think about how acidification works. There's different mechanisms for each gas. For ammonia, it's all about the chemistry. Ammonia is always in equilibrium with ammonium. Ammonia and ammonium are about equally divided when the pH is 9.3. If you drop the pH to 6.5 or lower, then almost all the total ammoniacal nitrogen will be in the ammonium form, which is aqueous and will not readily be emitted into the atmosphere. So that's where you want to be to conserve ammonia from being emitted. On the methane side, it's all about microbiology. Anaerobic conditions enables the methanogens to produce methane if the temperature is right and the pH is right and the substrates are right. So you can see in a farm manure storage, most of the emissions in a Canadian context would be in the late summer and fall and early fall. So adding sulfuric acid has the potential to reduce those emissions of methane. So what's the context in Ontario? How is manure being stored? I looked at the StatsCan survey from a few years ago, and the dairy farm responses are below. 85% of the respondents said their liquid manure storages have no cover. And of those that have covers, only a small amount are really designed in a way that might reduce ammonia emissions. So most of the emissions, most of the manure storages in Ontario have a high emission potential. Whereas in Denmark, liquid manure storages must be designed by law to impede ammonia emissions, either physically or chemically using acidification. So a big contrast there. So my research group over the last 10 years or so has been focused on measuring what the emissions are from Ontario and Canadian liquid manure storages. We use open path lasers that target the upwind and downwind sides of manure storages to measure the concentrations of methane and ammonia in the air, and we combine that with detailed measurements of wind conditions and turbulence. And with a dispersion model, we can determine what the emission rates are of ammonia and methane under natural conditions without interrupting the surface or changing the wind speed. So here's an example of a study we did at 4 dairy farms in Ontario with different management systems. The farm in the top left, their manure storage, an earthen manure storage, had a thick crust on it. They used wood shavings as bedding. And because of the thick crust, their emissions of ammonia were quite low in the summertime. So the ammonia is conserved in the liquid beneath the crust. the top right, we have a dairy farm with a screw press. It really doesn't have much crust, and so the emissions are higher, considerably higher than the first one. On the bottom left, we have a farm with a biodigester, but no screw press, so there's a bit of a crust there, and the emissions are higher again. And finally, with a biodigester and a screw press, we get the highest emissions of all, which is because there's no surface barrier, and the pH is higher, and the TAN concentration is higher. What about methane emissions? So this is one farm near Ottawa where we've measured emissions for a number of years, and we see every year in July, methane starts to rapidly increase. That's when the methanogens are starting to get active because the temperature is increasing. So we had the question of whether adding acid one time here, just before the onset of methane production, could reduce methane emissions. So could we end up getting this sort of horizontal line instead of this big peak? And this is different than the way manure tank acidification is done if you were trying to reduce ammonia emissions as your primary target. So this is more targeted at one intervention. We thought this is perhaps more achievable in an Ontario context where, you know, cost may be more of a concern, and we thought maybe this could target greenhouse gases with an ammonia co-benefit. So we did this at a research site that Rob Gordon established, and these 6 greenhouses are each sitting on top of a concrete manure storage, and each of those storages holds about 10,000 liters of dairy manure. And the chamber over top of it enables sunlight to go through to influence the surface temperature while enabling the airflow to be controlled, so we can measure the concentration of gases going in and coming out of the system, and using these sensors and acid traps to measure methane, ammonia, and nitrous oxide. So this is what the tanks look like on the inside. And Vera Sokolov did her PhD work on this at this research site, and published a lot of nice papers on this. On the left, you see the control dairy manure that's exhibiting a lot of bubbling, where methane and CO2 are being emitted. And on the right, the tank, one of the tanks that received sulfuric acid, has no sign of bubbling. And here's what the methane emissions that were measured look like over the course of summer and fall. So these are the 6 tanks with different amounts of acid that were added. And the acid, again, was only added one time, on one day at the beginning of July. And so the result over the course of the year was that the control tanks had the expected increase in methane and then decrease in the fall, whereas the tanks that had either amount of acid did not have any peak during the summer. So more or less 85% or better emission reduction, even though the pH decrease was not that large, you know. This was very promising. So the following study that Vera did was to look at how the gaseous emissions respond to different amounts of pH modification. So she added from 0 to 2 grams per liter, or 0 to 2 kilograms per cubic meter of sulfuric acid. And you can see that the pH decreased from around 8.2 to around 7.4. So it's important to note that although adding the sulfuric acid is decreasing the pH of the manure, it's not making it necessarily acidic in this case because of the pH that we started from. And so the ammonia emissions did decrease following a linear pattern, but methane was a little different. The emissions decreased linearly up until about 1.3 kilograms per cubic meter. After that, there wasn't really an additional benefit. So that's kind of the sweet spot, it looks like, for methane emission reduction. And that corresponded to a 20% ammonia emission reduction. So if you want more than 20% emission reduction, at least based on this study, you need to increase the amount of acid. So now moving on to field emissions. This is based on I'll start with a study that graduate student Lee Evans did. And she was working with Rob Gordon and Claudia Wagner-Riddle and myself. These wind tunnels were the tool that she used. Similar concept of measuring the airflow in and out, and the manure was applied inside this 1 meter squared area inside of the chamber. So what she did was took manure from 2 of the farms that I highlighted earlier, one with the biodigester and one with the separator, and applied the manure at the same time, at the same rate, broadcast on the surface and not incorporated. The first part of the study was done in the late spring when it was 20 degrees. And you can see just how fast the ammonia is emitted. Within the first day, the vast majority is lost. The second thing is how much higher the emissions were from the digestate compared to the separated manure. And that's the pH effect, as well as the increase in TAN concentration. The second part of the study was done late fall when it was quite cold, and you can see the patterns quite different, but the relative emissions are similar, with the digestate being higher again because of the pH. And in comparison to each of the observations, she compared it to a model, the ALFAM model from Denmark, which is based on hundreds of studies. And now it's been updated to ALFAM2, which I will use for some simulations in the following slides. It's a very user-friendly model and has a number of options for manure application methods that are quite relevant. So I wanted to find out how Ontario manure is applied. And again, the StatsCan survey has some interesting results. So how liquid manure is applied on field crops. Only 11% of the responses indicate what I would consider a low emission technique of injection or banding. 89% of the respondents indicated broadcasting, and mostly 1 to 2 days later or 3 days later, and then over 20% in the not incorporated at all category. And for forage crops, which was a separate question, 84% not incorporated. So the vast majority is broadcast and not incorporated. So what does that mean in terms of ammonia loss potential? Well, it means that the vast majority fall into the highest emission potential category, which in this scenario, kind of at 20 degrees, we're looking at over 40% of the TAN being lost. Now, if as the majority of field crops fall into this group of being incorporated after broadcasting, but after sort of 12 to 72 hours, there is a benefit from that. It does conserve nitrogen, but so better late than never. But there's a big benefit from incorporating within an hour or less. But that only represents less than 4% of the responses. So a lot of potential, I think, for acidification to help conserve nitrogen and make more available for crops rather than going into the air. So for instance, if we started off with a manure at pH 7 and broadcast it, we'd be looking at 40% TAN loss. If we decrease the pH to 6, then it'd be less than 35%. So a bit of a gain there. If we started from pH 8, it would be over 50% initially, decreasing down to the pH 6 would be a much bigger gain. But if we can acidify to pH 6 and apply with a trailing hose, which just drops the, prevents the manure from having to fly through the air, so it's putting the manure directly on the soil, then we get an even bigger gain. So the combination of acidification and putting the manure on the ground instead of flying through the air has a big effect in terms of how it conserves ammonia and gets it into the soil rather than letting it be lost into the air. So in summary, most of the manure, the liquid manure in Ontario is stored in uncovered tanks and earthen storages. And adding acid there can help to prevent methane. And based on the studies that we've done, it's possible to almost completely stop methane production, which can be a big benefit from greenhouse gas point of view, and to decrease ammonia emissions. Depending on the amount of acid, it could be 20% or more of a reduction. Most of the manure in Ontario is broadcast and not rapidly incorporated. So most of the manure is in a high emission potential category. And for this category, acidification can make a big difference. And if you can combine acidification with rapid incorporation or trailing hoses, that's going to be even better. High pH manure like digestate is particularly at risk of losing at least 50% of the ammonia when you consider the storage losses plus the application in the field. And acidification is a pretty well established technology in Europe, although it's geared at ammonia abatement, and there's a lot of policies that are driving it that are not transferable to Ontario. I think there's a lot we can learn, and I think I'm interested in targeting the methane as the first priority, and then having ammonia as a secondary benefit. But I think there's a lot that we can learn from that, and I'm looking forward to what comes next. So with that, thank you very much, and have a nice day.
Very good. That's an interesting start to our discussion today, and great to see some Ontario research on that. So Andreas and Vanya, we'll turn it over to you. Vanya, if you want to go ahead and share your screen, and you guys can carry on here and take the discussion in the context of Germany. And let me say, I do appreciate both of you being here. I know Germany time, I think, is what, 9 p.m. or so? So this is on your
7:30, so it's not too late.
Okay,
Andrew.
Very good.
Yeah.
It's not your bedtime yet.
Yeah.
All right, go ahead,
So,
guys.
It's perfect for us. Yeah, first I'd like to say thank you for giving us the chance to present the CyraN system, the system for acidification of liquid manure. We are very happy that there is many people interested in that technology. Regarding the agenda for today, I will have just a few words about Vogelsang, about the company where Vanya and I am working for. After that, Vanya will let us know about the technical details and about the chemical background behind. But about the chemical background, we learned already a lot. So I think he will do that very, very quickly. And when he's done with that, we will share some experience from customers from Germany and Denmark. And we will have also a look on a field test from the past, where we see the difference of stabilized manure with the CyraN system and normal manure. And also we will have a brief look on the economical things behind. So please go ahead, Vanya. Vogelsang GmbH und Co. KG. That's the company where we are working for. We are still a family-owned and operated business. Over the world, we are about 1,000 employees. 700 of them are working in the headquarters, what you see on the photo behind. and the rest is working in the 25 subsidiaries worldwide. We are not doing just agriculture. Agriculture is for sure one of the most important businesses for us, but we are also in biogas, which is sometimes very close to agriculture, but we do also wastewater, industrial applications, transportations. That is a business unit which cleans the toilets from buses and trains. So that's far away from agriculture. Just by the way, about the company. Regarding our portfolio for agriculture, the CyraN system is here in that picture. The last system. Beside that, we are the specialists for pumping, macerating, and spreading manure. So we do components for tankers, and I think the CyraN system is as well a component for a tanker. That's also an add-on. We do no manure tankers. Just for the information, we do everything around the technology around the tanker, pumping, spreading, but no tankers. That's not our business. So we deliver components. Then the question, how did it came that we have a cooperation that Vogelsang started manure acidification? That system was invented by a company called BioCover in Denmark, and they offered a cooperation in 2020 to us. And before we started that, we had a look, what are the results? Is it practical? How accepted is that? So we did a little bit of research on that, and then we figured out that it fits very well in the Vogelsang portfolio worldwide, and it makes sense to have that in our product range. It's a nice add-on for tankers, and it makes absolutely sense to use that in a combination with our dribble bars and trailing shoe booms. So that was the reason why we started that cooperation and why we started making the CyraN system finally in 2020. So the result effectiveness was not a question for us in the beginning. 130 users in Denmark said that works fine and we can handle that. That was a reason for us to say, we trust on that. That will work in other areas as well. Also, some pioneers from Germany were using it. There is a large contractor in the north of Germany who did many, many years promoting the CyraN system, and he's also absolutely convinced. He makes events where he invites his customers to convince them doing a better job on spreading manure. And we had a look at him up front, and that was all very good, and process costs are also okay, and that was the reason to start that as well. Then the guys behind the system, on the left side, there is Harald Vogelsang. That's the owner of the Vogelsang company together with his brother. And on the right side, there is Morten Toft. He is the owner of the BioCover company, and he invented the system in Denmark. And stabilizing NH4 in slurry, that works very simple. We have also seen in the previous presentation, you just need to lower the pH level, and that's nearly the secret behind. So very, very simple at the end of the day, the system, but the technical details behind are sometimes not so easy. Vanja will tell us that now.
Yeah, thank you, Andreas, for this first introduction of Vogelsang. Yes, let's now look deeper into CyraN system and, of course, the chemical detail. That's good that we had the first speech of Andrew via video, where many of these parts were also already prepared, so I can really run through this very quickly. And then we will, of course, have a deeper look into the technology of the CyraN system. So this will be the main part of my speech today. So, but first the chemical part, again, a little bit deeper. How does acidification lead to better nitrogen utilization? So as you know from the first video, in addition to ammonium, nitrogen is also present in liquid manure in the form of ammonia, NH3, and both compounds are, as my pre-presenter described, in the chemical equilibrium. So I showed that in that bar here. And if now the NH3 emits over time and becomes a monetary loss, and so also an environmental problem, the chemical equilibrium will then transfer further ammonium to ammonia, and the fertilizer value for the crop is lost. So this is a kind of a vicious circle that more and more nitrogen will leave the slurry due to the fact that we have this chemical equilibrium existing. And this equilibrium can now be influenced by the pH value. And if the pH value drops, as you can see it here in this little animation, the balance shifts towards NH4. So that means, as a result, less NH3 is emits and the liquid manure is acidified, and so it is finally stabilized. So here on this graph, we can really see the effect. So here we have a biogas digestate with a pH value of 7.8. When you look back to your chemics lessons, pH value of 7 is neutral, like blood or pure water. If it is higher, then we have a higher one, and if it's lower, we get to acidic one. So this one is still higher than neutral. So, and if we can see here the NH3 concentration in the air, and if we now use the acidification from pH 7.8 to pH 6.2, for example, here the red one, you see that the NH3, so the ammonia emission, really decreases over time, and then when the slurry gets to the soil, then it gets lower. So here, this is a real proof that acidification works in regards to lower the NH3 emission. So beside pH value, several factors play also a role in ammonia emission. So we have the temperature and we have the wind speed. This is what German fathers would call liquid manure weather, when it's 5 degrees cold and light rain. This is perfect weather for spreading manure, because then the ammonia emission is not that high. Of course, the type of liquid manure plays also a role, as well as the application technology. It's different if I use a broadcasting technology or incorporation, for example. And as my pre-presenter Andrew already told, there is the ALPHA model, a big European Union research project with a big database of emission data, and our cooperation partner BioCover has visualized this. So when you have this link, I think we can share it after this event here, then you can calculate your NH3 emissions specified for your weather data, for example. So we use, for stabilization, we use sulfuric acid, because it's a very efficient acid, and it has another nice feature if we use this acid. So, and to understand this, we have to look to this reaction formula. So the chemical equilibrium between NH4 and NH3, which we had in this bar graph in the last slide, we can see here as a reaction formula. And what happens if we add now sulfuric acid? We see here the reaction, and then we have the ammonium and we have sulfate. And sulfate is very nice for us, because this one is usable as a sulfate fertilizer. So that means if we use acidification of the slurry with the help of sulfuric acid, we can do completely without mineralic artificial sulfur fertilizer, because the sulfate being added by the sulfuric acid is completely enough to feed the crops. And maybe you're wondering, where does the sulfuric acid comes from? So sulfuric acid is not an acid being just produced to get the acid. It is more or less kind of waste product. Of course, it's no waste. It's a nice resource, but it is, for example, is produced during the mandatory exhaust filtration to avoid acid rain. So, and the manure stabilization leads to a higher utilization of nitrogen, and this higher utilization of nitrogen you can even see in the crops. So here we have a test field of the Agricultural Chamber of Lower Saxony in the northern part of Germany, and they made a trial. So this is completely the same crops, and the fertilization situation is completely the same, total equal values, but one without acidification and the other one with acidification. So this difference you can see here clearly is just reasoned by the higher nitrogen utilization due to acidification. And talking about acidification, we have to keep in mind that not all slurry is the same. We have differences in pH value and in acid amount. So here we can have 3 different groups. We have the fermentation residues, we have cattle manure and pig manure. And you see here the pH value, and here the added volume of sulfuric acid in liter per cubic meter, but it is per mil. So it is easy to understand. And we see here, for example, the fermentation residue starts with a very high pH value of 8. Then you just need to add 1 or 2 per mil of acid, and then the whole pH value will decrease very quickly. And then you can see here on different types of slurries. So every color mentions a different type or on another probe of slurry. And then you see after this very quick effect here, that then the effect gets very lower and lower. The cattle manure has a completely different behavior, more or less linear, as you can see here. And pig manure is very different at all. So there are some who are reacting in the behavior comparing to the fermentation residues, and others are a little bit more linear. So this is very important, that we cannot calculate this acidification. It's a biological process, more or less, and every liquid manure is different. So we have always to a little bit try and error to get the perfect dosage of the sulfuric acid. So that's for the chemics. Now the technical details. Let's look into the technology supplied by Vogelsang. So the design, we have here this front system is the front unit, which is more or less the heart of the whole Siren N system, and it's placed in the front because here we have the optimal weight distribution. Then we have some special hoses for the sulfuric acid, which lead the acid to the mixer, and the mixer is a place where the acid will be injected into the stream of liquid manure. And then it's a very quick reaction, and after that the acidified slurry will go the traditional way through the boom to the precision distributors, and then to the different hoses. On one hose, we have the so-called pH sensor box. It's a little box where the pH sensor is placed, and this one is responsible for controlling the dosage of the acid. So if we look to the structure of the front unit, here you can see the structure. In the center, we have a receptacle for an IBC tank, which contains the sulfuric acid. So it's more or less, it works like a fork lifter, so you can lower it down and then swap the IBC tank. And here you can see now the schematic top view. So in the center, we have this IBC. Then we have side tanks for additives. You can see here, for example, nitrogen inhibitors or some different additives which can be added to the liquid manure. We have a side tank for water. This for rinsing purpose, for safety purpose. So if you want to swap, for example, the IBC tank, you should rinse the whole system with water, that no sulfuric acid is in the hoses. We have the pumping unit for the acid dosing. It is a hydraulic driven pump. And then we have a safety package with gloves, glasses, and some other safety equipment. And we have a camera system for overview and safety. So in Germany, it's needed by law to add this camera system looking to the left and to the right to join the traffic with this system. And we have a third camera that you really easily can swap the IBC tank. Then in the rear of the whole tanker, as I said, we have this this mixer unit here. So here you can see that mixer with the injection nozzle. The acid injection nozzle is controlled by the pump in the front unit. And here you can see a cutted view. So we have some sheet metals which create turbulence in the liquid manure flow, that the whole acid, which is here presented by the blue lines, is mixed very nice and evenly, that it can then go to the dribble bar. Then the pH sensor box, which is in one of the hoses of the bar. So here you can see this pH sensor, and this one is built into a box. And this sensor controls the acid flow. And you can also have a documentation about the applied pH value. So you can use some maps for showing the applied pH value. Very important using or talking about Siren N is that safety is a very important topic, because as you maybe know, sulfuric acid is a very corrosive one. So it's definitely no apple juice. And so for us, it's very important to really offer a safe system. And so the whole system is closed. So there is no situation where the user will get in contact with the sulfuric acid. The only little chance is when you swap the IBC tank, and this is why you should wear your safety equipment with glasses and gloves during this change. Therefore, you have the safety kit. Of course, every time when you swap something, or if you want to disconnect the tractor, you have some water for automatic rinsing and washing. And of course, very important for us is that every user gets a training before using Siren N. So we always say, don't be afraid of the acid, but you always have to work with respect. So work with focus and be aware of the whole topic, working with corrosive materials or corrosive liquids. Yeah, the control feature of Siren N is based on Isobus. So we have an individual computer, an individual ECU in the front system. We have a communication via Isobus with a tractor. So therefore you can use your existing terminal, or you can have an independent terminal on request. And then we have two different application modes for the acid dosing. First would be the pH value fertilization, where the user says, okay, I want to go down to, for example, pH 6.4, and the system will calculate automatically the dosing of the liquid manure in dependence of the slurry flow rate. Or more or less the half automatic mode is the so-called sulfur fertilization, where you have fixed acid dosing. So for example, 3 per mil or something like this, in dependence of the slurry flow rate. And then you have, via this whole control center, you get a documentation with a special web app where you have a little GPS antenna on your tractor, and then you can have nice maps with the applied pH value and the applied amount of liquid manure and so on and so forth. So the whole system is also ready for digitalization. Yes, and now I would like to give the word back to Andreas, who will now present a little bit about Siren-N in the practice, case studies from Germany and Denmark. Andreas, you need to.
Sorry,
yeah, perfect.
sorry. Yeah, thanks, Vanya. I think now we know how the system works, and yeah, now we will share two customers' opinions from Germany and from Denmark, and yeah, we will have a look on a field trial from the from the Chamber of Agriculture in Lower Saxony. Siren-N in practice, there is many happy customers who are working successful with the system already. On two of them, we will have a look now. In total, there is about 150 units applied in Denmark, are running most of them, and Germany is just about to start right now. So the positive practical results from the German Chamber of Agriculture, I think they show that the system is easy to use and that there is also a benefit for the farmer, not just for the environment. So I think using the Siren-N system is, at the end of the day, a win-win situation. Dennis Struß from Germany is a contractor who wants to go ahead with the system. He is contracting since about 25 years, is a medium-sized company with 10 employees. They do forage harvesting, liquid manure management, and precision farming. And for him, one of the reasons was to use nitrogen in his manure more efficient, or in the manure of his customers. And he's convinced that the system pays off, where the fertilizer audience restricts and where it is not allowed to spread as much nitrogen fertilizer as you want. So in Germany, there is many reasons where we have problems with too much nitrogen in the groundwater, and you cannot spread as much manure or as much artificial fertilizer. So especially in these areas, it gets very important to use the fertilizer you have and you are allowed to spread in the most efficient way. And that is for sure one of the reasons for him. And also he saves the sulfur fertilization. He does that with sulfur acid inside the manure. So regarding the costs for him behind, he charges 45 cents per liter of acid. That is a average price in Canadian dollar cents, roughly. Some customers buy it cheaper, some buy it more expensive. Generally speaking, you can say when you buy a whole truckload and fill it in the small IBC containers, it's cheaper. When you buy just one container, it's probably more expensive. And the price goes up and down these days, like the prices for nearly all materials we are using on a farm. So he is using around 2 liters of acid he injects per cubic meter. Like Vanya said, that is 2 per mil, and he roughly reaches a pH level between 6.3 and 6.4 with that. So that helps to reduce the ammonia emissions a lot. So the total cost is roughly close to 2 euros per cubic meter for manure, per cubic meter manure for the acid and for the technical equipment. The slurry output, he spreads about 2,680 US gallons per acre. And the customer costs for the system is about 23 Canadian dollars per acre, we calculated. And that includes 26 pounds per acre of sulfur fertilizer, what you get for free. What he appreciated is there is a stable demand from his customers. So and the stock of plants develops better with the sulfuric acid than without, compared to and using sulfur fertilization with artificial fertilizer. So he has a better result when he is using acidificated manure instead of using artificial sulfur fertilizer. That's what he figured out. The next guy we like to talk about quickly is Jens Jürgen from Denmark. He is a farmer since 24 years, 100 cattle, 2 employees, and part-time he's working as a contractor. So he spreads slurry for other farmers in Denmark. And the reasons in Denmark are a little bit different. Denmark has more restrictions, so there it was just allowed to spread manure with the dribble bar when you were using the CYRA-N system. That is a difference compared to Germany, where this system is not obligatory. So they had the choice when they want to use the dribble bar with the large working width. They need to use the CYRA-N system. If they are not using that, they have to inject. Jens Jürgen is using a 31 cubic meter Tridem tanker with a 36 meter dribble bar system retrofitted with the CYRA-N. 36 meter, that's about 118 foot, I think. So yeah, he organizes everything, just in time delivery of the acid to the field. He pays about 20 euro cents for the machinery costs and 25 euro cents per liter of acid. So that's everywhere a little different. And he charges the sulfuric acid according to the consumption in liters per hectare what he needs. And yeah, the amount of acid differs from 1 to 3 liter per cubic meter, or from 1 to 3 per mil. The CYRA, yeah. So, and he uses 50 tons or for 80,000 cubic meters per year. Yeah, now we like to have a look at the practical results from the Chamber of Agriculture in Lower Saxony. That's the state where Vogelsang is based. And they made a trial on a reference plot where we were fertilizing with artificial fertilizer. You see it here, we started close to 100 pounds per acre. And when with different trials, it went up to 312 pounds per acres. I think it was 100 kilos per acre and up to 350 kilos per hectare, sorry. So the original trial was in unit was in hectare, and we calculated that to pounds per acre. Then the trial with manure we did with a dribble bar system, what you see here on the right side. In the center, we did it with a trailing shoe system, what's in the middle, and with an injection system. And the manure was spreaded on winter wheat in the springtime. So these days, roughly, of the year in 2019 to 2021. Yeah. And what we figured out is that we have a better result. We compared injection. So when you see the alpha model, what Vanya and Andrew mentioned, injection is on the same level with manure acidification when it comes to nitrogen losses. So we compared dribble bar and trailing shoe system with and without acidification with the injection system. And we figured out that this acidification makes a difference. So on the dribble bar trial, we had 98 bushels per acre in the average winter wheat. And when we used the dribble bar with manure acidification, it was 110 bushels per acre. In this trial, we did the fertilization just with purely organic fertilizer. So there was no artificial fertilizer involved, because the goal was to see the difference of the CYRA-N system. And yeah, when you want to figure that out in the best way, you need to test it just with organic fertilizer. The same result, or a closer result, we had with the trailing shoe. The reason for that is probably the trailing shoe does a little better job than the dribble bar. So it makes smaller stripes on the ground. The surface is a little lower, and that is probably the reason why the results are pretty closer. And with the injection, we got also 103 bushels per acre just with purely organic fertilizer. So it makes a difference. That's the difference regarding yields. Now we want to see what the economical things are behind and what costs the system for the farmer or the contractor. And the system costs, the original trial was in the picture on the right here in German. We transferred that to Canadian dollars and acres, and the costs for the CYRA-N system, that is an average value. So when you use the system for 500 acres per year, it's probably higher than when you use it for 2,500 acres per year. So that 11 Canadian dollars per acre is an average value. So we need 11 Canadian dollars per acre for the system. And for the acid, we need in the average another 90 Canadian dollars per acre. And the total costs are 30 Canadian dollars per acre of the system. That's what it costs for the farmer. The costs for the user of the system. On the other hand, we have cost savings from less artificial fertilizer because we do a better job using our manure or using the nitrogen inside the manure. So we save roughly 27 pounds of sulfur fertilizer times 34 Canadian dollars we've figured out. We hope that this fits also in Canada roughly. And that means we save 9 Canadian dollars per acre on sulfur fertilizer. And on the other hand, we calculated with a 10% better nitrogen utilization of 150 kilos, and that was per hectare, but doesn't matter. So we get another 15 pounds nitrogen per acre, and we calculated with $1.50 Canadian for 1 pound of nitrogen. I hope that this fits. If not, we have to recalculate that. I mean, these days the prices for fertilizer are very high, but yeah, that was overtaken from our values here. And we figured out that we get another 22 Canadian dollars per acre by saving nitrogen, and the total savings are about 31 Canadian dollar at the end of the day. What is not calculated inside is the potential extra yield and the higher quality of the crops. They are not taken into account. So on the slide before, we've seen we get some bushels more per acre, and that's why the system pays off at the end of the day. We save costs for sulfur and nitrogen fertilizer, and we get some bushels more per acre. And so that's how the farmer and the contractor can pay the system at the end of the day. By the way, there is also some side effects, not just for the wallet of the farmer. It makes also sense for the environment. We stop eutrophication. So we are not transporting nitrogen into lakes and moors where we do not need it, where it destroys the environment. We have it on our field where the plants can need it to grow. I think that's, by the way, a very positive effect. And that has also taken into account. Yeah, that's from us regarding manure acidification.
Excellent. Thank you, gentlemen. And Vanya, maybe I'll just ask you to stop sharing for a moment. I am going to put up the QR code here for the CEU credit. And I know technically we're at the end of our time here, but we're going to continue the conversation here. There are some questions in the chat, and we do want to share those as well. But I'll just put up this QR code for those of you who are obtaining a certified crop advisor credit. I'll leave that there for a minute or two. Guys, just to set the stage here a little bit, and I'm also going to ask Chris Brown. Chris, if you could bring your video and audio on, I'd like you to join the conversation too as we discuss this. Andrew in his presentation mentioned Ontario, primarily we have open manure storages and we have application to fields with not incorporation. Can you just clarify the German context? I think it's a little bit different, but what's the situation there in terms of open storages and how the manure is applied to field, whether it's incorporated, broadcast, or always injected?
Yeah, most of the manure we spread in the springtime and do side dressing. So I think that is not so common in North America to spread manure on growing crops, but in many parts of Germany that is currently the standard system, that you go with a dribble bar or a trailing shoe boom or a disc injector, whatever, and put manure onto growing crops. And that is the reason why we need that kind of spreading technology. When you do that with a splash spray, the weed grows very, very uneven. And yeah, you see that on first sight that this is not like you want it as a farmer when you do side dressing with manure.
Right, right.
When it comes to injection, that gets more and more popular. So the disc injectors to inject manure also in crops on grassland, we see that the market for that is growing here in Germany.
Okay, interesting. And as you commented, fertilizer prices, it's even hard. As soon as you put a number on paper, it's out of date these days. It's very difficult to stay on top of that, but it is dramatically changing the way we value this product, the product manure, and the way we have to calculate costs on these things. I just want to clarify a couple more things. You talked about the trailing shoe application, and some people may not be familiar with that. Can you just explain what that is? I know you had a photo there, but what's the quick explanation of the trailing shoe?
Yeah, that is the one step more sophisticated than a dribble bar. A dribble bar is just a hose where we do band spreading with. And the trailing shoe does a little better job. That is a small shoe that splits the plants, weed, grass. We are not working in the soil, that works on the surface, but it puts the plants away and places manure underneath the plants on the soil. So we have not so much manure on the plants, we have the manure on the soil. And at the end of the day, when we spread manure and when we want to reduce emissions, it's all about the small stripes. So we have to reduce the surface. And that's what the trailing shoe and the disc injector does a little better than the dribble bar for sure.
So this trailing shoe is made out of iron, so it really presses on the soil and it will cut the soil a little bit, not as much as the disc injector does, but a little bit, and so it has a higher utilization in comparison to the dribble bar.
Okay, and just one more clarification. Back a few slides earlier in the chemistry section, you were talking about fermentation residues, and I just asked you to clarify what you're referring to when you say fermentation residues. You also had cattle manure and liquid hog manure, but just so we have the context of what you mean by the
fermentation residues. So this is biogas substrate. So if I spread my my products from the biogas plant, we call them in Europe fermentation residues, because you have made this fermentation process on this this liquid, and so this is biogas substrate, exactly.
All right, so we would call that digestate in a lot of cases here in Ontario. Super, appreciate that. All right, I want to go to the chat because there's some questions there, and we'll hit them first.
Sure.
Couple of questions around the impact to soil. Okay, so could be particularly if you're working in acidic soils, but in any soil, the impact potentially to the biology because of the addition of sulfuric acid. Could you comment on that?
Yeah, so the impact on the soil is not a problem at all. So there were tremendously different research works, especially on Danish researchers, but also on Portuguese ones and German ones. And so especially the pH effect on the soil is not that different to the effect you have when you use artificial sulfuric acid, artificial sulfuric fertilizer, because
So
if you add
commercial fertilizer, as we would say. yeah.
exactly, this one will also lower the pH value in the soil a little bit. And we see when we use acidified slurry or acidified liquid manure, it will be more or less the same. And yeah, it's always a kind of thinking about it. So if you hear, okay, we acidify now the slurry, then everyone thinks, oh, we will now put acid to the soil. But the reason for thinking this, and I thought this as well when I started thinking about this whole topic, the reason for that is that we are not that familiar with this pH scale. So this one is, and as I presented, we will lower the pH value from, for example, 8 to 6.4, and when you have the rain falling on your soil and falling on your fields, it will have a pH value of 5.5. So it will lower the pH value in the same amount as the acidified slurry does. So this is very important. But all in all, it's comparable to artificial fertilizer. Yeah.
Okay, all right, very, very good. And maybe at this point, following up on that, Chris, I'll pull you in to comment on this. But here in Ontario, we closed the coal plants. All the coal plants we had by the end of 2014 had to be closed. And Chris, that's had some impacts in terms of sulfur in our crops and so on. Can you make some comments on that, Chris? And I know you referred to that a little bit, Vanya, as well. But Chris, comments on that.
Yeah, we've seen over the past few decades that because of the reduction of the coal-fired plants and the reduction of acid rain coming from the U.S. side, that we've had to start using more sulfur for some of the crops. And it's hard to say which crops respond the most from a crop-to-crop basis, but canola and alfalfa and wheat specifically have seen responses to the addition of sulfur. Corn not quite as often, soybeans not quite as often, but definitely alfalfa and canola. And so some people will say, well, yeah, but my manure is adding sulfur as well. But I think it's important to know that most of the sulfur in manure is an elemental form, and the elemental form is a slow release form of sulfur, similar to organic nitrogen, where the sulfur that's being added in commercial fertilizers like sulfate or ammonium sulfate or some of those products, and same with what would be added in this acidification process, would be in an immediately available form of that sulfur. And typically, I think our crops it's changing over time, but about 20 pounds per acre seems to be the number that most crops respond to where sulfur is added. And I know there's some other people on the call that might have more exact numbers, Jeff Bannerman and some of the consultants.
Okay, speaking of Jeff had an interesting question. Can we add the sulfuric acid to the tank to reduce the pH in the tank and therefore stabilizing the tank loss? Comments on that?
Yeah, that is something we did not mention. When we inject sulfur acid into the manure, it gives a reaction and the volume extends by a factor 2 roughly. So that is why we have to inject it into the manure flow just a few meters before the implement. So that wouldn't work because the volume extends in the moment where you inject sulfur acid, and it can be by factor 2. So 1 liter manure gets 2 liter manure with a little foam. That means the tanker would explode if you put it all inside.
But if you would, you could also acidify your, so as Andreas said, you cannot add sulfuric acid to a closed system. So if you have a closed tanker, this is not possible. I don't know if maybe the question leads more to the storage of the liquid manure. This one would be possible. Of course, you can. So what we do with Siren and System, we apply the sulfuric acid directly before spreading the liquid manure on the fields. But of course, you could also use it for, during the storage of the liquid manure. Then you would definitely lower the emission level again because you start earlier in the process, you know. This is possible, but you have to look on the economical side, because when we decrease the pH value in the storage, we have to keep in mind that the liquid manure has something like a buffer. And this chemical buffer will bring up the pH value after several weeks. So what happens, you have to add more and more acid, you get more and more sulfate as well, and somewhere there's too much sulfate, and you need tremendously more sulfuric acid, and then the whole economical business plan, so to say, could be a little bit weakened. So this is why we say we use acidification directly during spreading, but there are some systems in Europe to have it in the storage as well. Yes.
Perfect. I'm curious about the efficiency, energy efficiency in particular. So you're using the dribble bar, you're doing a surface application, you're pulling that equipment, as opposed to the incorporation. Any comments on the efficiency differences there, and if that comes into play with the economics?
Andreas, would you like to answer, or should I
Yeah.
answer?
You mean the efficiency between a dribble bar and the trailing shoe boom, or what?
Yes.
Or which between what?
Yeah.
Yeah.
And the incorporation as well with the coulter and so on.
I think one of the reasons why we use the trailing shoe and the dribble bar is while we spread manure on standing crops, and then it's not so easy to incorporate it with tillage equipment. When we spread manure in the summertime on the stubble field, where it's not allowed to spread much manure in Germany anymore, so it's just allowed to spread manure when there is something growing in field. When there is nothing growing after harvest, we cannot spread much manure anymore. But then it's also common to incorporate it directly when we spread a little bit manure on the stubbles. But when the season starts, like now in February or March, we have to do side dressing. And yeah, the trailing shoe boom and the dribble bar do on wheat, barley, on standard crops a very, very similar job. I think when you spread manure on alfalfa or on grassland, the trailing shoe has an advantage. It does a better job.
Okay. You mentioned.
Can I answer that too? Just
Yeah.
on the economics. I think one of the reasons that I think the system has a lot of promise is because when you look at a dribble bar, it's got a boom that's similar to herbicide applicators, where you've got 60, 90, 120 foot boom. You're spreading potentially a lot more acres with manure without having to do the injection, without the compaction, without some of those other issues. And so I think that's, as soon as we look at injecting manure, especially traditional injecting that we do in Ontario, it takes a lot more horsepower, it takes a lot more time to cover the same acres. So I see, especially when you can go in crop application into alfalfa, or this time of year into wheat, that it has a lot of potential time savings and even compaction and horsepower savings, fuel savings.
Super. And thanks, Chris. And I do want to mention in the chat there, my colleague James has put in a comment that about 30% of Danish pig farmers acidify the pig slurry directly in the storage tank. So that's an interesting comment to add to the previous discussion there for Jeff's question. Guys, I was interesting. You talked about the emission calculator, and yeah, do send us that link. That was interesting. Chris, for you, can you comment on work in Ontario? Have we got some stuff going around emission calculators, and is there something to come down the road?
That's a great plug, Andrew. Most of you know about the AgriSuite tools, and the AgriSuite tools include the manure calculator and the field management plan calculators and MStore. But there's one that's in the works right now where we're looking at relatively simple, based on the HOLOS model that they have in Agriculture and Agri-Food Canada, mostly starting in the West. But there is a greenhouse gas calculator that's being added to the AgriSuite suite of tools, I think later this summer. I think that's the goal. or maybe it's early summer, but sometime this year. And it's going to be relatively simple, just comparing different management systems to say, okay, am I reducing carbon emissions, not giving the exact pounds, because I don't think we can calculate those details yet. So stay tuned.
Perfect. I'll just mention too, Andreas, thanks in the chat for answering Chris's question, which was around the cost. You said 23 per acre. Chris was asking, is that just the cost of the sulfur, or does that also include application? And you clarified that is the total costs for the system. So
Yeah.
Appreciate that.
That was the total cost from the farmer in our example. It depends. Vanya has shown some examples, especially on digestate. We need a lot of acid to bring the pH level down. On other manure, you need maybe just 1.5 or 2 liters. Then the costs are lower. And the costs for the equipment, if you share that by many acres, it's less than when you have just a few acres to do with it.
Yeah.
So
perfect. Appreciate that. So one final question here. Appreciate you staying overtime with us, guys. One final question is future work. What's next? What are you working on? What are the questions that you need to get answered? What's the plan?
I think we will. So we will definitely look deeper on this acidification topic. So in Germany, as Andreas presented, it still starts, and I think worldwide we will see that in future. And this is why Vogelsang will definitely put more development effort in making this even more usable. For this system is for now more or less for big contractors having a lot of acres. So we definitely need one system for smaller farmers, especially here in, for example, southern Germany, and for Europe as well. And of course, we see some trends on injectors and trailing shoes in Europe. And yeah, there we will focus on new developments, and of course looking to the other side of the Atlantic Ocean, to the US and to you guys in Canada, how to better understand what's going on in these markets, how we can help to have a better nitrogen utilization over there. And yes, this is more or less Andreas and my job to get this analyzed and then develop the perfect equipment working on your fields as well. Yeah, this is my perspective as a product manager on our future in agriculture. Yeah.
Andreas, any final comments from you?
No, that was very good. I want to mention that we are also based in North America. We have a daughter company in Ravenna in Ohio. So there is Vogelsang based in North America. Canada, we handle with agriculture directly from Germany. That's why we are here. On the other side in the States, our colleagues from US are responsible for agriculture sales.
Wonderful. And I know at this point in time, I know there's at least one system operating in southwestern Ontario. So I think Chris and I have a field trip this summer sometime. We'd love to get out and see that system working. But just as final comment, I do want to mention again, we also appreciate Andrew Vanderzag, the video he sent, and you can email questions to him, andrew.vanderzag, and that's Zag with 2 A's, at agr.gc.ca. So feel free to reach out to him if you have questions there. But Andreas, Vanya, and Chris, thank you very much for joining us today. We appreciate your feedback. This has been a great session. And folks, as we wrap it up, just a reminder, next Monday is the final Manure Monday, and we have another great session, and we'll have John Lozon, who's been a favorite of Manure Mondays, and he is talking about black gold, and that is maximizing manure nutrient utilization. So join us again here, same place, same time next week as we have our final Manure Monday. Cheers all.